You all semua dah buat clearance college ke? Clearance college dah buat ke?
Dah.
Okay, good. So, saya ada yang nak masuk. Okay, right. Let's join us. Oh, Carlos. Okay. Hi, Carlos. Carlos Angelo Navarro. How are you today? Okay, good. How about the rest? Another, your colleague, is it they will be join us or not today? Okay, I will be continue. Okay, question 1C. Okay, Aisha is here. Okay, let's madam. Where we are? Okay. Okay, let's try see this one. With the aid of a diagram, how the mechanism can be replaced with a suitable sensor. Okay, you have to introduce one type of sensor to convert pressure to output voltage. Okay, so for this example, I give you burden tube. Okay, let's say we have a burden tube here, and then the output to burden tube is a pressure. Okay, pressure. Okay, and then the output is a displacement, right? So how the burden tubes workings, you all, everybody can refer to our notes or YouTube, okay? How the burden tubes workings, the working principle, okay? So when we apply the pressure here, okay, you can see the arrow here. When we apply the pressure here, so this C curve, okay, we can see the C type. Okay, actually this is a burden tube, and then the type is a type C. Okay, okay, so you can see when we apply the pressure through this tube, so this curve will be extend. Alamak, ramai lah flight join hari ni. Geng-geng Filipin dia join. Okay, Mark here, and then Adrian here. Okay, let's continue our just a bit information how you can answer our past year paper. Okay, this is a little bit on we discuss for question 1C. Okay, now we discuss question 1C. Okay, let's I introduce back. Okay, you have to explain how this mechanism can be replaced with a suitable sensor, convert pressure to output voltage. Okay, this is a burden tube. Okay, the output for burden tube is a displacement. Okay, and this is a mechanical transducer. Okay, this is burden tube is a mechanical transducer, and then the output to the mechanical is a pressure, right? Okay, when we apply pressure to this curve, okay, this curve will be extend, okay, and then meaning the output when we apply the pressure, the curve will be extend, meaning there will be contribute the displacement. Okay, this one we label with the X. There will be and then this area also will be extend. Okay, and then the output is the extension, we call it displacement, right? And then you have to introduce another one transducer to put here to get the output is a electrical signal. Meaning electrical signal, for this example, we need the output from this transducer as a voltage. So you have to choose one transducer and apply in this question mark. Okay, so I need everybody find out what is the transducer you will propose here. Okay, what type of transducer you have to propose here? So meanings here is a displacement. Okay, and then you have to introduce one electrical sensor or electrical transducer here to get output is a voltage. Okay, gamma Ashraf here. Okay, so that's okay. So that's about question 1C. Okay, I need everybody try answer. Uh, Discuss first. You can discuss among your classmate, okay, what type of transducer suitable you apply for this uh, question. Okay, this one electrical, you have to choose one electrical transducer. Okay, you have to choose one electrical transducer. The input is a displacement, meaning from here. Okay, just now this one. Okay, this block, okay, the output displacement, okay, and the output we need to convert pressure to the output voltage. Meaning just now the input to the burden tube, okay, this is the example is a burden tube, okay, and then output from the burden tube is a displacement, and then you have to introduce one transducer to get output voltage, meaning the electrical transducer convert displacement into voltage. Okay, that's about question 1C. Okay, let's question D. Question D. I think this is we already discussed from our previous tutorial. This is more or less with the previous example. Okay, previous our tutorial. Okay, please try first for question 1D. Okay, now let me see question 2. Question 2A. Okay, question 2A is on our topic control system, okay, on our control system, introduction about the control system. So you can refer from that one, meaning um, this example is a water level, is a water level control system. Okay, so from this case study or from this process, you have to represent the functional block diagram. Okay, you have to represent the functional block diagram, and then you have to label what's the input and output to the system, and then the controller, where is the actuator, what is the actuator, what is the plant, and what is the feedback element. Okay, from this example, from this water level control system. Okay, that's 2A. And then we see question 2B. Okay, question 2B. Uh, this is actually a ladder diagram or ladder network uh, system. Okay, and then all the equation is given, but when you plot the construct block diagram, this equation finally determine the transfer function. Okay, from question 2B, we cancel out. Okay, this one no need. Okay, this one we cancel. Okay, question 2B, and to see the same system, the kind of system mathematic derived. Okay, this one also we have to cancel out. Okay, 2B and 2C cancel. Okay. Oh, this is in a flow graph. Um, okay, signal flow graph. We can proceed signal flow graph. Wait, I see the example. This one, share and share. Okay, we can. This one we can. This is as environment outside. Okay. Okay. Question 2C. We we can proceed this one. Okay. So this one okay. You can do it. Only we cancel out is this one. Question 2B, no need to proceed. Okay. 2C is a signal flow graph. Okay. So if you refer figure 2C, okay, if you refer figure 2C, you have to draw the signal flow graph. Okay, from here, you have to draw the signal flow graph, and then from there you have to define the transfer function. Okay, so you have to define the transfer function. The first one, you have to define uh, from here you have to define two type of transfer function. The first one, you have to derive a transfer function for this one. Another one is a y over r. Okay, which one is the open loop? And then from the block diagram also you can put a comment which one is open and which one is closed loop transfer function. Y over e, y over r. Okay, you have to define the transfer function. The first one is a y, represent your output. Y over e, and what is the transfer function? Another one is a y over r. Y is the output. Okay, this is your output, right? Okay, and r, as you know, our input, and e is the error. Okay, and from first you have to uh, draw your signal flow graph. Okay, from the signal flow graph, you have to determine the transfer function. Okay, but so you have to follow the step by step uh, to define the transfer function using signal flow graph. You have to define the loop, the forward parts, and you have to define the what some more forward parts. You have to define the loop gain, and you have to define the non-touching loop gain, and etc. Okay, once you complete, uh, you can answer the question. The last row. They ask you what is the which one is open loop and which one is a closed loop transfer function. Okay. Actually, from this block diagram also, you can see which one is a open loop or which one is a closed loop. Who can tell what is which one is a open loop system and which one is a closed loop system? Who can guess which one? Y over E, Y, what is a Y over E? Is it open loop transfer function or closed loop transfer function? Who can guess? From the block diagram, actually, you can guess which one is open loop and which one is a closed loop. Who can share here? Which one?
Y over E closed loop.
Y over E. Where is our E? E is here. Normally closed loop. Macam mana kita dapat closed loop?
Have feedback.
Ah, okay. So meaning Y over E closed loop or open loop? Y over E. So kena
Open.
Open.
Y over E is open, right?
Y over R
Okay.
close.
Yes, very good. Y over R is closed. Okay, because Y over R, you have to minimize this feedback, unity feedback, right? Is Y over E, you don't need to minimize the unity feedback because E is here, R is here. Okay, nampak tak? You can see it, which one is open loop transfer function and which one is a closed loop transfer function. Okay, that's for question 2C. Okay, now we see question 3A. 3A, this is the performance. Okay, they ask you what is the damping ratio and how does it affect the transfer response, stability, and steady state error of a control system. Okay, so how many um, type of damping ratio? We can classify the second order to how many type of damping ratio? Siapa ingat? Kita ada berapa damping ratio? We can category, okay, from the, we have a closed loop function. Okay, we have, ada berapa damping ratio? Syah, ada berapa damping ratio? Kita boleh kategorikan.
Hmm.
How many damping ratio we have? How many category? We have berapa? 1, 2, 3, 4, 5. How many type of damping ratio? We can category.
Ada tak ingat.
Alah, tak ingat. So,
Empat ke? Empat.
yes, 4. Yes, we have 4, is it? Is it? We have 4, kan? Okay,
Yes.
Oh,
the first one, damping ratio. Let's say like example, equal to 0. Lagi apa?
Mm,
Ha,
More than one.
more than one. Lagi?
l-
equal to
less than between less than one and more than zero.
Okay, another one. Di satu apa? Ada
equal
ke
to
yang less?
zero.
Ada
More
tak?
than
Ada tak yang less than one? So this one you have to refer notes.
equal to one.
Okay. Ha?
Equal to
Equal to one. Ada ke?
Ada.
Ada.
better.
E1.
Okay, equal to 0, greater than 1. This one betul lah ni.
Hmm.
Okay, ni betul. This one.
Betul.
Yang ni,
Ada
Equal
yang ni
to.
equal.
equal.
Hmm.
Okay. Okay, so we have 4 types of damping ratio, and then from damping ratio, you have to explain what is damping ratio. Okay, you have to read what is damping ratio and how damping ratio will be effect to the transient response, stability, and the steady state error. Okay, this is you have to refer maybe your textbook, okay, to find out the answer for this one, right? Okay, now how about B? B is characteristic of unity. Okay, B. Okay, this is soalan soalan Ruswitz kan? Okay, evaluate the settling time. Okay, for this question uh, consists of time domain. Okay, okay. Untuk soalan 3B ni, this consists of 3 chapter. Okay, this is consists of time domain. Time domain, we can divide into 2, right? Transient and steady state error. Okay, so you can see from this example, we covered on the settling time. Settling time is you have to analyze what? Settling time, peak overshoot, and then steady state error is a ESS. Okay, for settling time and overshoot, okay, this is under topic transient. Okay, and then steady state, and then another one, stability using Roots-Hewitts criteria. Okay, from that system, there we covered 2 topics, time domain and Roots-Hewitts. Okay, but before that, you have to know this is considered is a analysis. Okay, the first one you have to change the damping ratio using 0.7. The second one, and then what the second one you have to replace damping ratio equal 0.4. Okay, so meaning you have to calculate 2 times. You have to calculate your setting time, peak overshoot, and steady state, and the stability using this damping ratio. Okay, and then the second one, you have to calculate you have to evaluate all the parameter uh, given here with the damping ratio 0.4. Okay, using this system. But before you evaluate, you have to know to evaluate time domain. Okay, you have to define closed loop. Okay, you have to define your closed loop transfer function. Okay, this is you have to bear in mind. Okay, and then to evaluate steady state error. To evaluate steady state error, you have to define G your GS. Right? You have to define your GS to evaluate steady state error. What is your GS in unity feedback? Okay, that's you have to represent this figure into 2 types. You have to represent this figure in 2 conditions. The first one, you have to represent the closed loop function to calculate or to evaluate your time domain. Okay, for how to evaluate the steady state error, you have to represent your block diagram in terms of GS, in terms of remember how to do your error. Okay, this is your R input, output, and you have to find out your G. This is your G, right? Just now, this is your G. Okay, H is you already got, or you already in unity feedback. Okay, so be careful for this question. Okay, the first one, to evaluate time domain, you have to represent your system in terms of closed loop function. Okay, the second question, you want to analyze the steady state error, you have to represent your system is similar like this. You have to define what is a GS. GS is this A and you multiply with the B. So you can get your GS here. Okay, now you already simplify your block diagram and then you can answer the question. Okay, evaluate. You have to evaluate the parameter using two conditions, damping ratio 0.7 and damping ratio 0.4, and then from there you have to conclude. Now see, for your calculation in B, decide on the preferred damping ratio to be used. Okay, you have to decide based on what? Settling time, overshoot, and error to be used and explain why. Okay, this is you have to see. Um, Supposedly for this example, okay, for one system is a good, or for the one system we say is good on the stability when they have a fast settling time, okay, or short settling time and very low overshoot, and also the steady state is very close to zero. That's the very good damping ratio. Okay, so from your calculation, when you use damping ratio 0.7 and after that you use damping ratio 0.4, you see what is the time settling there. Okay, you have to see what is the settling time. So if this one you have to answer first, so you can compare which one settling time is much better, the shortest or the fastest settling time. This is a good for stability. Okay, and also you have to see the peak overshoot. Okay, the very low peak overshoot, the very low percentage, this is a good system. And same goes to steady state error. The error, which error or whose error close to zero, this is the good system. Okay, so for this example, you have to calculate first and substitute the value of damping ratio with in the two condition, and then from there you see what the settling time. Okay, you see the settling time, the peak overshoot, and the steady state error from the two condition. Okay, damping ratio 0.7, damping ratio 0.4. Okay, that's for time domain. And then now we also use the same system, define the stability using root service. Okay, this is also same goes. You have to define the closed loop transfer function, and then the second one apa? Table. Okay, roots table. Okay, from the roots table, so you have to define whether they have what, the sign changes or no sign changes. Okay, let's use the root switch to define the stability. Okay, that's for question apa tu? For question 3. Okay, that one is for, sorry, hold on, for question 3B. Okay, so question 4 is a bot plot. Okay, question 4 is a bot plot. Everybody familiar how to make magnitude, how to plot magnitude and phase right now?
Yes, medium.
Very good. Everybody fingertips how to draw. magnitude and phase on the semi-log graph paper. Hmm. Semua dah terror ke? Dah buat plot. Adrian, Ariel, Aina, Faika, Hakim, Hidayah, and siapa lagi ni? Jaidi, Mak, Joshua, Naima, Farhana, Aisyah, Nani, Din, and Shamidi. Everybody fingertip about the board plot. Is it?
Boleh lah, madam.
Okay, very good. Okay, now let's see. Question 4. Okay, question 4, we have two conditions. Okay, the first one, k equal to 10. Okay, for the next question, the increase instead of k equal to 10, the increase the value gain k into 100. Okay, the first one. Oops, sorry. The first one. Allah, mana ni? Okay, the first one is k. K equal to 10. Okay, the second one, they increase k to equal to 100. Okay, and then you have to conclude the stability of the system. Okay, meaning the first one, if k equal to 10, you have to construct your board diagram, meaning you have to plot your magnitude versus frequency. Another one, you have to plot phase versus frequency. Okay, and then from the plotted, you can answer question B. Okay, so you have to define the stability based on what? Based on your phase and gain margin. Okay, that's for when k equal to 10. And then when we increase k to 100, so you have to define how effect to the stability, whether the system stable or not when we increasing value of gain k. Instead of 10, we increase into 100. Okay, so from this question, actually you no need to calculate all those slope. You no need to redo your table. Okay, because the value change only k, but you use the same system. Okay, we use the same system, and then the the changing only for k, and then for board plot, we use value of k to define apa? Untuk define apa untuk k ni? Siapa ingat? Untuk define apa? Phase or magnitude? Which one? Magnitude.
Magnitude.
Yes, very good. Magnitude. So meaning we use k for starting magnitude, right? Okay, so example. So let's say this is example, right? So let's say the first one, example, let's say k equal to 10. We begin 20 log 10 and 5. We begin at 20 log 2, right? So meaning about maybe 6, is it? And then after that, we plus with the j omega. I think this is a similar with your previous exercise. Okay, and we add another 20. So let's say this is 26. Okay, this is for begin 26 when k equal to 10. Okay, when k equal to 100, so when k equal to 100, we cancel out with the 5, you can get 20 log 20. 20 log 20, I think 26 Cuba seorang tekan calculator. 20 log
Yes.
20. Okay, 20. Okay. So plus with the S. So we can get 46. Okay. So meaning when K equal to 10, you begin magnitude begin at 26. Now, when K is 46, let's begin at here. This is a K equal to 100. Okay, so meaning how about the difference between this? About 20 dB, right? Okay, about 20 dB. Okay, let's say this is your magnitude graph. Okay, this is a magnitude graph. Okay, let's say madam sketch red color. Okay, we start at the for K equal to 10. They start at 26. Okay, when K 100, they start at 20. They start at 46. The difference is about 20 dB. So meaning this red curve, you shift up about 20 degree here. Abang, bateri tak ada. Kejap ya, bateri low. Okay, we shift 20 dB onwards. Okay, this is for K equal to 100. And then every corner frequency we shift up 20 dB. Okay, let's say from here. Example, okay. Example, this is the corner frequency is a 5. We shift up this one to here. About 20. From here, about 20 dB. Okay, and then we get the new, and then we sketch. Okay, we sketch. And then let's say this is also, actually we have a two corner frequency, right? Okay, this is our K equal to 100. Okay, this is how we want to define the plot plot if only value K is changed. Mana? Sini. Okay, thank you. Okay, alamak, hilang. Okay, dapat tak apa yang madam nak share dekat sini? Kalau K berubah, K instead of K equal to 10, so K jadi 100, you tak perlu, no need to start again your table because K only effect to the K only effect to magnitude, not for phase. Okay, phase tak berubah pun. Okay, so cuma instead of K 10, begin dia berapa? Okay, the next one for K equal to 100, you find out the new begin. Okay, the first one begin 26. Okay, you sketch at the red curve, and then the second one, the different 26 to 46 is about 20. Okay, this one 20, and then this one also you shift up about 20 dB per decade, and then this is our new magnitude plot. Okay, so this is our new. And this is our new plot. Okay, any question for this board plot? Ada soalan tak?
Jadi
Ada.
maksudnya 4C tu kita kena lukis untuk graf magnitude je lah.
Ya, you kena define graph magnitude saja, and then phase dia sama. Lepas tu you proceed yang sama juga. So when magnitude is changed, so of course your your gain crossover also akan berubah kan? Okay, so you can get the new phase margin. Okay, and then using the same phase crossover, and then you akan dapat new gain margin. This is you akan dapat the new information. Okay, the new information, this one, and this one. But this is guna K equal to 10. Okay, but because the magnitude is, you have the new graph of magnitude, right? Of course, your gain crossover different. And then phase margin also different. And then gain margin also different. Okay, because the cutoff here is a different, right? Okay, this is your phase crossover yang baru, yang for the new K, right? Magnitude, we still refer the old one, the old one at the step A. Okay, because magnitude, phase only, phase start dekat mana? Kita punya phase start dekat mana? Our phase start using J omega kan? Okay, our phase start with this one, right? So you don't need to sketch. Kalau you nak lukis balik pun tak apa, tapi buang masa lah. Okay, that's why saya suggest you satu graph untuk phase, lagi satu graph untuk magnitude. Sebab bila value of K ni, when K is changing, there will be change your magnitude. Because the system sama. Sistem kita guna yang sama, cuma K saja berubah. Okay, ada soalan? Any question for this board plot?
Madam,
Ya.
saya ada confuse sikit
Hmm.
mengenai WGCO dengan WPCO, macam mana kita nak dapat? Maksudnya kadang-kadang terbalik-balik. Semula dia macam mana supaya kita nak cari dulu?
Okay, sekejap ya. Magnitude, frequency, and then this is a phase. Okay, so let's say this is our magnitude, and then our phase maybe like this. Okay, ni contoh je ni. Okay, right. So for omega G CO, G ni adalah gain. So this is your, this one. Okay. So let's say your gain crossover here. So you have to find out value apa kat sini? Value omega. What's the value omega here? Okay, this is your gain crossover frequency. Okay, for gain crossover frequency, you refer back to phase with the same frequency. Okay, this is your okay, ini adalah alamat. Aku tak boleh tulis ni. Okay, ini adalah your phase margin. Okay, using gain crossover frequency, kita akan dapat phase margin. Okay.
Okay.
Dengar tak?
Okay, dengar dah.
Okay. Now, untuk dapatkan lagi satu PCO, untuk kita define gain margin. PCO ni maksudnya phase crossover. Okay, this is your phase crossover. Okay, this is your PCO. Okay, PCO ni kita dapatlah berapa dia punya omega dia, berapa radian per second. Okay, and then kita guna the same omega and then cari dekat sini. This is your gain margin. Okay, clear tak Din?
Oh, okay, clear. Okay.
Okay, alright. So kita nak define whether our gain margin positive or negative, face margin positive or negative. You have to refer to our notes Okay, ni refer notes. Okay, refer note tu lagi clear. Note yang saya bagi tu. Right, macam mana nak define face margin and gain margin. Right. Okay, that's how to define the stability using box plot. Any question so far? We finished our set June, right? Sorry, June 19. Any question so far? Is it so far so good? So far so good? Ariel? Andrian?
Yes, madam.
Okay, right. So please try our first June 2019. Okay. Now we see which one? December 19 and December 18. Okay, question 1. With the aid of diagram, okay, this is a kacang This is okay. This is a quite simple, right? Straightforward. Okay. December 18. Ni tulis ni. Dia jadi intermittent. Tak apalah. It's okay. So we go to question number 1. Okay. For December 18. Question 1. With the aid of a diagram, you have to show what's different between accuracy and precision. We have to give, or you have to illustrate the diagram for accuracy using what? Bull eyes. Okay, you have to use bull eyes to show how the accuracy looks like and how the precision looks like. Okay, you have to give in the diagram to explain the differentiate between accuracy and the precision. Okay, that's for question 1A. And then for the next question, how can we measure this parameter from the measurement data? Okay, this is you have to find out from our lecture note or from the textbook. Okay, that's for question 1. Dah tak boleh tulis dah bang. Dia intermittent. Tak apalah, biarlah. Okay, question 2B. Question 2B. Okay, a sensor pressure transmitter tekan kat sini. Boleh pula.
Jangan tekan
Oh, okay. Okay, for just now, okay. Question B. Okay, this is okay. Okay, question B. Sensor measure temperature linearly with a static transfer function. Okay, let's say from here. What is the transfer function? 33 milliwatt over degree C, right? Okay. A sensor measured temperature linearly with a static transfer function of 33 milliwatt over degree C and has a 1.5 second time constant. If the output is measured 0.75 seconds after the input was changed from 20 degree to 41, find the error of the measure temperature. Who have the idea how to solve this example? Siapa ada idea macam mana nak solve soalan ni? Anybody have the idea how to solve this example? Siapa boleh bagi tahu? Any idea? Term function T3 time constant. Time constant equal to 1.5 second. And then output measured. If the output measured 0.75 second after the input was changed. Okay, the temperature change from 20 to 41 degree C. Okay, this is let's try first, okay? Let's try first and after this we discuss, right? Okay, how about C? Explain the temperature effect on the strain measurement using metal strain gauge. Okay. Propose a solution to minimize this problem. This is also you can refer our notes, right? How temperature effect to the strain. Okay. And then how about D? D is this is reflect to the gauge factor. Okay. This is actually the simple. This is a straightforward question D, right? Show the relationship between resistance change and strain. Okay. And then determine the resistance. Okay, this is you have to answer 2 times. The first one, you have to determine the resistance change using gauge factor 2.13. The second one, you have to choose gauge factor minus 151. When strain is given and the nominal resistance for both strain is a 120, meaning this one you have to define what's the value of delta R. Okay, you have to define the resistance change using two condition this gauge factor with the same strain and same nominal value, but you have to define the delta R in the two condition gauge factor. Okay, how about number 3? If the metal strain gauge is used to regulate a strain 1450, construct a DC bridge that the bridge is null at this condition. Okay, the number C, you have to construct your bridge. Okay, our input, this one, you have to draw your bridge. Okay, this is your way out. Okay, and then which one you want to allocate your strain gauge? Maybe here. Okay, this is your strain gauge. Okay, let's say you have to choose your which one you want to label R1. Maybe this is R2, and maybe this is your R3. Okay, you have to uh, construct your DC bridge. Okay, such that the bridge is null at this condition. Okay, that's for uh, part 4. Okay, any question for that? Number 1. Alamak, mana ni? Ayo, sekejap. Dah lari ke? Ayo, ayo, ayo. Mana ni? Okay, any question? Is it okay? Not yet. Okay. Now, question number 2 is a functional block diagram. Apa dia? Macam ni. Okay, question number 2, functional block diagram. Okay, so you have to define what is the input output and what's the actuator, controller, plant and the feedback element. Okay, question 1A and question 1B. Okay, question 1B, this is a modeling. Okay, this is a modeling. How to define the what angle over we input. Okay, you have to define angular replacement over input. So meaning this is your output and this is your input. Okay, from here you have to still remember how to solve this example. Okay, meaning for this part, for the mechanical part, okay, for this mechanical part here, okay, so meaning your mechanical part is a TS in terms of S domain, in terms of domain, meaning you can define as a JS squared plus ds plus k and multiply with the motion. Okay, with the motion. This is because this is we assume series. Okay, in series. So we just multiply all this one. Okay, to get the total of torque here. Okay, and then this we have a motor. DC motor. DC motor should be they have to derive what? Two equation, right? First you have to derive torque proportional with the current, right? With the IF. Oh, this is not torque. Oh, yeah. Torque proportional with the IF pula. IA. Okay, torque proportional with the IF. Okay, only one because this is a field control DC motor. Okay, and then IA constant. Okay, so meaning you have to define the equation related to motor is a torque proportional with the IF. Okay, right. Okay, the beginning. Apa boleh buat kat depan ni? Your KA. Okay, KA. What's the relationship here? Hmm.
Eh?
Yeah. So, kita kena define amplifier dulu. Okay, you have to define amplifier. Kan dekat sini ada amplifier satu equation. Okay, so meaning amplifier output dia adalah VF. Kan? Output equal to gain KA multiplied with the input. Remember tak? Output
Yes.
equal to gain multiply with input. Okay, you have to represent, follow this standard equation. Okay, VF output from the amplifier and input is the VI is the input into the amplifier, and then from here you have to, that's another equation you can derive the field circuit. Okay, so meaning from here you have the one equation for the amplifier, one equation for field circuit, and then one equation from the motor, this one just now. Another one is the one equation from the mechanical system. Okay, and then from there you derive an equation and then you come out with the function individual block diagram. Okay, and then last one you have to draw complete block diagram. Next you derive what's the transfer function. Okay, angular displacement over V in. Okay, that's for question B. Any question so far? So far so good?
Good.
Okay.
Good.
Okay, this is number. Mhm. Ni apa soalan dia ni? Signifograph eh? Okay, during focus is integrated. This one, okay, this is a signifograph. Okay, this is a signifograph question. Okay, this one. Okay, you have to draw your signifograph. Okay, and then how many knots actually we have here? Okay, this is knot 1, this is knot 2, knot 3, knot number 4, knot number 5, knot number 6, and then this is knot number 7, and this is knot number 8. Okay, so we have 8 knot, and then you have to do your, let's say 1, 2, 3, 4, 5, 6 here, and 7 is here, and 8 is here. 1, 2, 3, 4, 5, 6, 7, and 8 is in between 4 and 5. This is number 8. Okay, so you have to prepare the note for your signal flow graph similar with your label here 1 and until 8. Okay, from there you give one here for input, another one here for your output, and then from there you have to label 1 to 2 is here, right? Okay, and 1 and 2 to 3, this is a G1. Okay, 7 to 2, this is 7 to 2, like this. Okay, 7 to 8, what is 7 to 8? G3 and G5 are central, and then 8 come back to 7. This is H1 and the rest. Okay, right? Got idea how to solve question C? Okay, very good. Okay, let's number 3. Number 3 is a for time domain. Okay, this is everybody know this is a general second order. Okay, general second order closed loop transfer function. Okay, the question is describe with illustration for 4 possible transfer response of a second order system as a function of damping ratio. Okay, so meaning we have a 4 type of damping ratio. So you have to illustrate in the graph how the graph looks like. Okay, to represent for each type of the transfer function. Sorry, each type of the damping ratio. Okay, that's straightforward, right? Question A. Let's see question B. This is a question B. Okay, question B, they give you apa? Dia bagi you all apa? A position servo mechanism can be modeled using a second order model in figure. Figure question 3 show the pole zero map on the S-plane. By referring to the pole zero location, okay, mana pole zero location you? This is your pole zero location. So meaning this is the pole. Allah Akbar. Sorry Apa benda ni? Okay, this is the pole. Okay, so from the pole, so they also provide the like the label here -6. Mana? -6. Okay, they provide this -6 and this one and this one. This is a complex number, right? They will give pole here. So meaning, let's say this is your S1, this is your S2. Okay, so this is your you can to you have to refer to our notes. What's the label here? -6 equal to what? Equal to sigma, is it? Minus 6. Minus 6 equal to sigma omega n ke? Siapa boleh tengok? Sigma multiply with omega n Dia lupa lah. Minus 6. And then for this one, for J6. J6 equal to apa? Apa label dekat sini? Can you refer to our notes? J6 equal to what? J omega or what? This is you can refer to your notes, okay? So and then let's say you already know the value of S1 equal to minus 6 minus J6 and S2 equal to minus 6 plus J6. Okay, this is a pole. Okay, pole for the system. Okay, this is the system. Okay, this is the system. Okay, so from the system, to evaluate our pole and zero, you have to define your closed loop transfer function. Okay, the first one. Apa soalan ni minta you? The first one. Construct the open loop and the closed loop transfer function of the second order system. Okay, meaning the first one, you have to feedback this part first. Okay, number one, you have to feedback this part first. Okay, lepas tu, after that, you multiply with the K1. Okay, let's say here, we simplify here, you can get A, example, right? This is equal to A. And then, after that, to simplify, you will get K multiplied with the A. And the diagram, you can get like this. This is your output. And this is your input, right? Okay. And then from here, you have to define the closed loop transfer function because this is to define the pole zero, right? And then you have to define the settling time and etc. You have to define the closed loop first. Okay. Define closed loop. Closed loop meaning CS over RS equal to what? Okay, you have to simplify this feedback to define the closed loop transfer function. Okay, define closed loop function. Right. Once you get your closed loop function, you compare with the pole given. You have to compare with the pole given. Okay, and then from there you can get the unknown value. You can get what is a K1, you can get what is a K2. Okay, you can get here, but you have to compare first the closed loop block diagram from this one, compare with the pole given. Okay, then you can get the value K1 and K2, and then after that you know how to solve settling time and peak time because from when you get K1 and K2 you can get what's the value of omega n and what's the value of a damping ratio. Okay, and then from there you can calculate your settling time based using your formula. Okay, that's for question 3B. So how? So far so good? Still can follow our discussion? Okay ke? So far. Any question?
Okay, madam.
Okay, so let's try Okay, next. Ni apa? Steady state. And now Russowitz. Okay, this is a Russowitz. Okay, Russowitz where they give you the two condition. They give you two condition of gain. one K, another one EKH. Okay, this is also you have to define your what? Identify that open loop and closed loop system stability is dependent on the value of both K and KH. Identify the open loop. Open loop meanings, let's say like I give you this is a A, okay, and this is a B, right? Open loop is a B over A. This is the open loop transfer function, okay? And for closed loop transfer function, C and R, CS over RS equal to closed loop transfer function. Okay, you have to define two conditions. Okay, and then you can answer this one. Identify the open loop and closed loop system is dependent on the value of K and KH. Meaning you have to comment what's the effect value of K and KH in two conditions during open loop and during the closed loop. Okay, and number two, you have to define the stability. Okay, of course, for stability, you have to represent your system into the closed loop transfer function. Okay, that's everybody know, right? To define the stability using root switch, you have to define first the closed loop function, meaning you have to define this condition. Okay, you have to use this condition to define stability when K is given. K5, another one K equals 0.5, sorry, 0.1. Okay, that's for question C. Uh, for question, yeah, for question C, right? Okay, clear? Din, boleh follow tak Din? Aisyah, boleh follow
Okay,
tak?
okay, tapi
Tapi confuse sikit kan? Tak apa, cuba dulu. Try dulu buat. Okay, you all try dulu. Next session, discuss balik apa yang you all figure out whether you have a having problem to solve this example and etc. Boleh? Kena try dulu. Kalau tidak, tak tahu kat mana problem you all nanti. Okay? That's why saya nak cuba and then you all baru akan find out where is the problem happen. Dekat mana yang which topic yang you all tak faham. Okay? Faham tak? Okay, faham tak?
okay.
Okay. Aisyah? Okay ke? So, di mana kita sekarang? Di mana kita? Okay, ni question tadi. Bruce Willis. Lepas tu, the next one is the
Question 4.
dot plot kan? Question 4. Okay, question 4, dot plot. Okay, dot plot ni frekuensi 10, frekuensi respon dia bagi open, dia bagi this one, dia bagi forward gain. Okay, this is a GS. Lepas tu apa lagi? K10. Okay, this row you buat plot. Okay, the question give K equal to 10. Substitute here. This is also familiar. Same as your previous question, the previous paper, and same also with your example in our class. Okay, K equal to 10. Construct your block diagram using the asymptote approximation method, macam yang kita dok buat lah, uh, using our method. We define the GH S, and from here we change into J omega. Okay. Okay. kita dapatkan GH J omega. Okay, that's for question 1. Okay, B, from the plotted, determine gain crossover, phase crossover, and acentra. Okay, and conclude the stability of the system. Okay, from the plotted, determine this one. This is considered another exam, another question. Okay, you have to determine this one, value K, to obtain gain margin 20 and phase margin 21.5. Okay, this one, how to define the new K when gain margin 20 and the and phase margin, the new gain margin and the new phase margin. Okay, this is I will share uh, share recorded video sebab it's a quite difficult to explain. Okay, I have to show you on the semi-log graph how to show, and then how to determine the value of K when the gain margin 20 and the phase margin 21.5. Okay, for this example, you have to plot your graph and then define the stability. That's for the normal case using the table and etc. But this determine the new K when gain margin 20 and phase margin 20, 31.5. I will be share later. Okay, how to define the value of K, right? Okay, C. Okay, C, this is a night quiz. Night quiz is we are not covered in our topic. Okay, night quiz is we cancel out for this one. Okay, we not covered night quiz in our syllabus. Okay, that finished. Last paper. Last paper. The last paper, January 18. Okay, January 18. This is also similar with our previous tutorial. Remember RTD? We use the table. Okay, this is a straightforward. Define the meaning of transducer and acentra. This is a straightforward. Everybody is a fingertip. How to define the transducer? Okay. How to define transducer? Explain the principle of availability. This is also to our refer to our notes. Okay. And this is also refer to our notes, right? And then C, draw Wheatstone bridge, state a condition for a bridge to be considered and balanced, right equation. Okay, this is also refer notes. Okay, and D, this is same with our tutorial. Okay, and then you refer back to our previous tutorial how to solve question 1D. Okay, so the next. Okay, question 2B is a functional block diagram. Okay, question 2B, functional block diagram. Okay, question 2A, sorry. 2A is a functional block diagram. Question 2B, this is a schematic diagram of a DC motor. It consists of a mature control DC motor. Okay, this is sama juga. This is same with our notes or same with our example during our meeting. Okay, derive the loop of the armature, meaning armature back MF VB to EA, and another one is a direct equation related to back MF to the motor rotation, meaning the theta M over theta B. Okay, another one is a use KB by MF. Derive the equation of the armature circuit that relate the back EMF to armature. So meaning the first one, you have to define the relationship between the VB and EA. Okay. So for the easy way how to solve this example, you have to derive one by one. You have to derive the equation. Okay, the first one, you have to derive equation what? Armature circuit, right? Armature circuit here. This is the first one. The first one is a armature, and the second one we have to derive the DC motor. Okay, DC motor contribute two, right? The first one VB, the second one is a torque. Okay, and then this is the what? The torque ni pergi mana? Okay, this is the torque. Okay, the torque here. Okay, this is a torque. Okay, this is a total of torque just now. Torque equal to what? Okay, the torque is this is the input. Sorry, yeah, angular is the input, and the torque is this is the output. Okay, you have to from this example you have to write equation by equation based on the question. Okay, based on the question, and then this is you have to solve the equation related between torque and angular. Okay, and then the last, the part 4, you have to what, the armature current and mechanical torque produced at the rotor is proportional and can be presented. This is the given. Actually the question is torque proportional with the IA, right? And then from here they simplify, you can get torque, and they give one coefficient constant for torque KT, right? Okay, when KT is a motor torque. And then the last one, you have to derive the overall transfer function. This is similar with our example. Okay, dekat dalam notes. Okay, this is similar with our notes. So this is you can refer to our notes, right? Okay, C. C also similar with the previous one. No, this is a Mason. Sorry, this is a Mason's rule. Okay, for Mason's rule, so you have to sketch block diagram. You have to convert into the signal flow graph, and then define the transfer function using Mason's rule. Okay, so let's say from here we have show closed loop amplifier tachometer respect K1, K2, whether to improve the control, derive the closed loop function of the system using signal flow graph. Okay, so meaning this is not number 1, not number 2, and this is also not number 3. Okay, so meaning we have not 1, not 2, not 3, and this is a not for output, and this is for our input. Oh my god, sorry. Okay, this is our output, right? Okay, and this is our input. Okay, from node 1, node 2, we have a K1 here. Okay, 2 to 3, we have motor. You have to write down what is the equation here, right? And then 2 to 3, this is 1, this is 2, this is node number 3. Okay, 2 to 3, we have a motor here. And then you have to write the equation. And then 3 to here, we have this one, we have a tachometer. And then another one, 3 back to 1. Back to 1, this is a minus, so meaning this is a 1, so meaning this is a minus 1. Okay, from here you have to define what? You have to define Mason's rule. Okay, you have to use Mason's rule. You have to use Mason's rule to define the jump function. Okay, you have to define your forward parts, you have to define your loop gain and etc. Okay, using Mason's rule. Okay, let's see question number 3. Question number 3 similar with our, is it similar? Hold on. 3A is explain the condition for a stable, marginally stable, and unstable by using pole analysis and roots criterion. Okay, this is for this example, you have to define using pole, how to define stable, marginally stable, and unstable using pole. Using pole meanings on the S-plane. Okay, how to define? Okay, where is the location of pole when if you want to show the system stable? Okay, and where location of pole for unstable and where the location of pole for marginally stable. That's using pole analysis. Okay, for using Rose-Weiss criteria, so you have to use what? So you have to define what's Rose-Weiss say to define stable, marginally stable, and unstable. Okay, for stable meaning no sign changes in the first column, right? Okay, for unstable, so how the condition Rose-Weiss mentioned, and for marginally stable, how the Rose-Weiss mentioned. Okay, for marginally stable meanings, you remember we have a special case. Okay, for special case is the condition uh, uh, to discuss or to explain about the marginal stable. Okay, meanings for special case we have what? Zero in the first column or entire zero in the first column, right? Okay, that's for special case to define the marginally stable for root width. Okay, for stable, so kena tengok lah. So kalau for stable meanings no sign changes in the first column, right? For unstable, have a sign changes in the first column. Okay, that's explanation for question 3A. Okay, for question 3B, a closed loop is given. Okay, this is already closed loop down function. Okay, if K, okay, right now also is this is also analysis example. Okay, K increase from where to where? K increase from 1 to 10. So you have to define the settling time overshoot. Okay. The first one, you have to calculate K equal to 1. The second one, you have to calculate K equal to 10. You have to calculate a settling time, you have to calculate overshoot, and then you have to make a comparison. Okay. If K allowed to increase from 1 to 10, find how the settling time and overshoot will change with respect to K. So you have to make a conclusion. Okay, when we increase K instead of 1 to 10. Okay, how you can conclude or how you can find out the effect of the settling time and effect of the overshoot when we change K instead of 1 into 10. Okay, that's question B. For question C, for the same system in B, calculate the steady state error if the input. Okay, remember for 3C, you have to define the error in term of TS. Okay, remember tak? We have a two method define the steady state error. The first one, ingat ke? Kita ada dua. We have two type to define the steady state error. To define the steady state error. First one, we define using the T term. Okay, we use the T term to define the steady state error. T term to define steady state error. The second one, we use GS term to define steady state error. Now, using the same in B, B is given in T, so you have to use this one to define the steady state error with the respective input is given. They give input 5QT, RT, and then this is a unit step, and then this is a RAM. When K equal to 1, when K equal to 10. That's given. UT is step and RT is RAM. Okay, this is also you have to find steady state error in two condition. K equal to 1 and K equal to 10. Okay, that's for 1C. We use T terms to define the steady state error. Okay, how about D? D is a root service. Okay, D is a root service. Okay, this is how to define the range of K. Alright, sure, the open loop system is always stable regardless of the value of K, but the closed loop system stability is depending on the value of K. Okay, for this one, show the open loop system is always stable. For always stable, so meanings this is open loop. Okay, the given, okay, they give you this system, unity feedback. So meanings, if we draw into the block diagram, H equal to 1, and they give you forward gain output, and this is the input. Okay, so this meaning show that the open loop is always stable. Meaning, what is the open loop? What's the open loop term function? Meaning, open loop term function is just GS multiply with HS equal to K over S, S plus 2, S plus 3. Okay, this is the open loop transfer function. Okay, from how to define the stability from this one. You have to define the location of pole. Okay, so you have to show that the open loop system is always stable because we define, you remember how to define the stability? Stability, we can define into two, we have two methods, right? The first one using pole zero plot, the second one using root width. Okay, meaning show the open loop system always stable, you use open loop plot. Okay, and then the second one is a closed loop, meaning we use RH. Okay, so you have to show the open loop system is always stable regardless the value of K. So meaning when we use stability using pole zero plot, we only define the stability using denominator, right? So meaning K is a doesn't affect. Okay, that's the question needs you to explain, right? You have to show this pole into the explain. Okay, meaning the K is doesn't affect because you find the stability just using your denominator. Okay, meaning you have to define pole because K is not related to open loop transfer function to define the stability. Okay, and then the second one, open closed loop. Closed loop meaning you have to define C over R. You have to simplify the feedback. Okay, so we can get the closed loop transfer function and then using rule width. Okay, and then of course using rule width, there will depends the value of K to define the stability. And then K is effect whether you want the system stable or you want the system unstable. Okay, based on value range of K, right? For B, part 2, evaluate the range of K to maintain the closed stability using Rosewich criteria. Validate your answer. Okay. Once you draw your Rosewich table, okay, and then you fill up the table, and then you can show from that table the closed loop is depending on the value of K, right? And for section 2, okay, from the section 2, you replace K1 and K40, and then you validate your answer. Okay, but before that, you have to evaluate the range of K to maintain the closed loop stability. Meanings, let's say the first one you can get plus plus or something like that. Okay, to make it stable. So K supposedly have to greater than zero, right? Okay, this is you can refer the notes for topic a range of K. How to define the stability during range of K. Okay. Then the last one, Allah, sekejap. Okay, the last one I think board plot. Okay, this is a board plot. Board plot ni apa? Unity feedback. Okay, meaning the H equal to okay, H equal to 1 eh? Okay, sorry, H equal to 1. So for question 4, H equal to 1, right? So meanings derive the analytical expression for magnitude and phase in the frequency domain. Okay, this is on theory. Okay, how to derive the magnitude and phase. Okay, you have to write the answer. This is a theory. Okay, how to explain, right? The second one, you have to sketch a night quiz. We cancel the question for night quiz. Okay, we just focusing on the board plot, right? Night quiz exam derivative plot, evaluate the range of K. That okay, this one we cancel out the question. Okay, okay, that's all. Any question so far? Ada soalan tak?
No, madam.
Okay, tak ada soalan. Okay, so kalau tak ada soalan, so let's try this. Sekejap ya, madam stop dulu record ni.